Hey there, everybody. How are my circular friends doing? Hope you guys are doing well. Um, we're gonna do circles and forces number 2 today, and it's gonna be a little different than usual. Um, for the most part, we're just gonna kind of work a problem, and it's one of those problems that should kind of give you a bigger picture and some practice. So you're definitely going to need some scratch paper to do some work. This is one of those you definitely don't want to just watch. You want to get involved and see if you can do this. So all right, here we go. We're still talking about circles and circles that are horizontal. So look at the picture over on the right. We have our velocity and we have our mass, and we have some kind of centripetal force. Um, Whether it's tires, the friction of tires when you're turning a corner, or something stuck onto a turntable, or a string spinning something over your head. We need some kind of force to make us go in a circle. Now, if you're in a car going around a corner and the corner is perfectly flat, that force is going to be the force of friction with the tires in the road. Um, and if you go too fast or you turn too sharp, that friction doesn't hang on anymore, and you end up sliding. You overcome the static friction of the tires, and you end up in kinetic friction world, and you skid in a corner. Now we're going to do today kind of a strange problem, but it's one that shows up a lot. The idea anyway. So we're going to do, well, let me just explain the problem first. We're driving along and we come up to a corner that's banked, and we go around the banked corner. So here's me in my car coming right towards you on this banked corner. All right. So the mass of my car is 1,000 kilograms. The bank is 10 degrees. The radius of the corner is 30 meters, and we're going to use 10 for little g today. All right. So now, here's what I'm going to say. Think back to the last picture, and the centripetal force was provided here by friction. So you can think of these force arrows as frictional force as well. I'm going to tell you something. What would happen if I keep my car pointed straight? I don't turn the wheels at all. I just drive like I'm in a straight line. All right. What I'm going to tell you is I would go around the corner if I get my velocity just right. So the question we're going to ask today is, what velocity do I need so that I don't have to turn my wheels? I don't have to use any friction from the tires. Now this may seem like a crazy problem, but this is why it seems to show up so much on AP tests, because the idea is a little hard. All right, so trust me on this one. Let's see if we can work through and do this. So let's do this. Let's draw a free body diagram of the car. Now, real quick, up until now, we have gone from things like period and velocity and speed all the way down to forces. We're going to go the other direction this time. We're going to start with forces, and we're going to move back towards velocity. All right? So we're doing just what we did last time, but we're going to go the other direction. All right? So let's see how this goes. So here I drew a free body diagram, and let me pull these axes right over here so you can see what I did. There's my car, and there's my X and Y axes. So think about this. If I'm going around a corner, let's continue the corner so it's like a track that's a circle. And what I'm telling you is I would just keep going around this track without even turning the wheel on my car. And you're probably thinking, yeah, right, Mr. Eiler, you've gone over the edge finally. You've lost it completely. But let's do this. So draw for me, or think with me about the free body diagram on the right. Made my car into a dot, and I have one force going down, and we're going to call that the force due to gravity. And the car is sitting on the road. So I have what we're going to call the normal force as well. Those are my two forces. Now, I'm not going to turn the wheels. So I'm not going to use any frictional force here, you know, like I'm making the car turn in any direction. I'm just going to go straight. Now look at that. The forces are not balanced. No matter how long or short I make those arrows, I can't balance them because one of them's tipped. All right? So let's have a look. What we normally do is we break vectors into their components. Now, Fg, the force of gravity, is right along the y-axis, but the normal force is not because the surface I'm on is tipped now. All right? So what I want to do is I want to break the normal force into two forces, and I'm going to draw them as green lines. I have the normal force in the y direction, and I have the normal force in the x direction. Now, let's think for a minute. Is the car going to fly up, straight up in the y direction, or straight down? No. It's not. So those two forces should balance, the force of gravity and the normal force that's in the y direction. But look, there's a force in the x direction. There's a component of the normal force pointing in the x direction. That's what's giving me the centripetal force to go in a circle. All right? So if the road is flat, that centripetal force comes from the friction of the tires. But now I don't need any friction from the tires because the bank itself, the tipped road, is going to push me in a circle. Okay? So the question is, we got to get to velocity. All we have is forces and a few numbers. Let's see if we can get to velocity. Here's what we're going to do. We're going to do Newton's second law in the x and the y direction. Let's do y first. Newton's second law. Sum of the forces in the y direction equals m times a in the y direction. And then next to it, okay, we'll draw a big line down here. We'll do the sum of the forces in the x direction equals m times a in the x direction. All right. Here's what I want you to do. Let's start with the y. I want you to see if you can do this for me. So first, fill in all the forces you can in the y direction. All right. And do m times a. See what you can do. Pause me and then move on. All right, let's see if I can do this. I have the normal force in the y direction minus the force of gravity equals m times a. Aha! A is 0 in the y direction. Whoops, should have written my y there. Okay? So let's pull gravity over to the other side. The normal force in the y direction equals force of gravity. Alrighty. Doesn't help a lot. We know what the force of gravity is. Mass times little g. But what's the force, the normal force in the y direction? I'm going to go back up to the drawing here. Look at this. We have theta and we have the normal force. So we have the hypotenuse and we have an angle. So is the normal force in the y direction sine or cosine? Figure that out. Okay, I think it's going to be the normal force times the cosine of theta. And in the x direction, we're going to have the normal force times sine theta. Did you follow that? That's our trig trickiness that we're always doing. Okay, same thing as we always do. We have our triangle and we just break it up into pieces. So let's make our substitutions. All right, we have the normal force times the cosine of theta equals m times g. All right. So, sorry about that. I had a little cough. Hopefully I didn't disrupt too much. Let's keep going here in the y direction. Let's get the normal force by itself. M times g divided by the cosine, cosine of theta. All right, I think you can plug in numbers. I did this earlier. I have an answer. I want you to do it before me and see what you get. I get the normal force is 10,152 newtons. All right. Now, you guys, sometimes you solve stuff and you're not quite sure where you're going to use it. And that's okay. So go ahead and do this. In this case, we got normal force, and you're thinking, yeah, so what? Whatever. Well, all right. Let's go over to the x direction, see if we can get anything. Sum the forces in the x direction equals m times a in the x direction. Fill in everything you can for that. Pause me while you do it, and then start me back up again. Alrighty, the sum of the forces in the x direction is the normal force in the x direction equals m, and we're on a curve, we're going in a circle. What is acceleration for a circle? V squared over r. How did you do? Did you remember that one? Alright, what is the normal force in the x direction? It is the normal force times the sine of theta equals m times v squared over r. Hey, look at that. I'm going to underline everything we have. We have the normal force from here. We can calculate the sine of theta. We have the mass. We have r. We only have one thing we don't know. And hey, guess what? That's what we were looking for in the first place. Right up here. So I want you to solve for V and then plug things in. Do that all and see if we get the same answer. So pause me while you do that and then start things up again. All right, here's what I got. Tell me if I'm right. I got a huge square root sign, and I have the normal force times the sine of theta times r divided by m. How did you do? Now, a lot of times, folks, we write this a different way. Let me rewrite this just to show you so you don't make a mistake. We'll write the normal force, and we'll put the r in front of the sine, because sometimes people will multiply the r and the sine together in the one above, or the r and the theta together in the one above before they do the sine, and that'll mess things up. Okay, and that's just a little neater way. Usually you put the trig stuff last. You don't put anything after it. All right, and I get 7.3 meters per second equals the velocity. Look at that. Wow, that's a hard problem. So there we go. We did the problem. Now, what I'm going to give you next is basically the same problem, but I did something. I left the mass off. Okay, so what I want you to do is to do this. Follow pretty much the same thing we did, and I gave you the steps, 1, 2, 3, 4, 5. Notice 5 is the only one that has any numbers in it, and I didn't give you the mass. So what should happen in the end is that the mass drops out. You don't need it. Okay? So we'll see if that happens. Hopefully it will. All right? And if it doesn't and I made a mistake, come yell at me tomorrow, and we'll definitely fix it. But see if you can do this one. We're going to be working with letters for a bit before we put numbers in. So hope you enjoy. Have an awesome evening. Bye-bye.